All right, so this video is going to be going over limits to infinity. So as x goes to positive or negative infinity, what is y going to? We want to look at this as the same thing as a horizontal asymptote. So if you have a number, an output, that your limit, your function is going to as you take this limit, then as you get really close to L, X is getting really close to whatever that A value is. So if we're letting X go to infinity, notice here in my graph of f of X, as X goes to infinity, this graph gets really close to Y equals 2, and it actually does so on both sides. So because of that, because the limit as x goes to infinity of f of x equals 2, and it does so on both sides, we say, oh, this must have a horizontal asymptote of y equals 2. And so that's going to be the definition we use for a horizontal asymptote in this class. As you go to plus or minus infinity, if you approach a solid number L, then that number must be the horizontal asymptote of the function. So let's go ahead and look at something like A. This is the parent function, 1 over x squared. It's got to flip. It's got to move up. All sorts of fun things are going on here. So let's go ahead and look at the limit as x goes to infinity of this function. So as x goes to infinity, I want us to maybe think of like a table of values here. And we'll first start with 1, just so that it's nice and easy. If I plug in 1, I get 5 minus 2, I get 3. If I plug in 10, then I get 5 minus 2 over 100. I'm purposely not going to simplify this, okay? If I plug in 100, I get 5 minus 2 over 10,000. And so on and so forth. So as x is getting bigger and bigger, as x is going to infinity, I'm going to have 5 minus something that gets really ridiculously small, or 5 minus 0. And so you'll notice that this ends up getting to like 5.000001 or something like that, or it gets really stinking close to 5. If I go to the other side, I notice the same thing. In fact, if I make these negative and square them, I end up getting the exact same outcome. So my horizontal asymptote for this first one must be y equals 5, because this limit must be 5. Now I'm going to do the same thing for C. And then we'll pull back and talk about B. So on C, I actually want to look at a graph of arctan first. So on this graph of arctan, let's first look at a graph of tangent. Tangent has vertical asymptotes at negative pi over 2 and pi over 2. And so arctan, if I flip this around, or flip it around the line y equals x is really what I'm doing, those vertical asymptotes actually become horizontal asymptotes. So as I'm taking the tangent, the inverse tangent, I should say, of numbers that are getting really big, my graph here is going to approach pi over 2. On this other end, as I have x values that are getting actually really ridiculously small, or big in the negative direction, whichever way you want to think about it, I get negative pi over 2. So I actually have two horizontal asymptotes. You have two end behaviors. Horizontal asymptotes, you want to make sure you evaluate on both sides, both positive infinity and negative infinity. And it is possible, because you're going on both sides here, that you could have two different end behaviors. Think about the parent function, e to the x. If you only ever talk about as x goes to positive infinity, you're not going to have a horizontal asymptote that you find, because the function values go to infinity. They don't go to a number. But if I evaluate the left-hand side, I see, oh, I do have a horizontal asymptote. It gets really, really stinking close to 0 as x gets really, really small or really big in the negative. So we might have one horizontal asymptote. We might have none. Okay, not all functions have horizontal asymptotes. Some of them go to infinity, but we might have one. We might have two, like in this example. But our last example, I want to talk about that sine of x over x example. We sometimes think about end behavior and the fact that like we can't cross it. And actually, if you look at this graph, and then I'll pull up kind of a table and we'll chat about why this happens. But a graph of this function kind of looks like this. And we do have an oscillating piece of this, but the oscillations get smaller and smaller and smaller. And so this graph actually does have a horizontal asymptote, because it has a limit. As x goes to infinity, the numbers get smaller and smaller and smaller. As x goes to negative infinity, the numbers get smaller and smaller and smaller. They get closer to 0. So it does have one horizontal asymptote. Both directions are the same, and it's at y equals 0. Numerically, why is that the case? Well, because sine is bounded. It is always a number between 1 and negative 1. You're then taking a number between 1 and negative 1, and you're essentially letting the denominator get really, 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 really large. Well, anytime you have a number over something that gets really, 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 really large, you're always going to have it go to 0. And you can plug in things, we talked about it in some of the other examples, but like 1 over a million is really small. So that's the sine piece, is why it's oscillating back and forth, but because it's over x, as x gets really, really large, both in the positive and the negative direction, the overall number, sine of x over that large number, will converge to 0 as you're going out to those ends on either side.